Okay, so module 10 is going to be our last module that we will be studying about. And even though we will not have any exam or any drill test uh, for module 10, you must know that it is a very important component of your final exam. Okay, so radical reactions. Before we go into radical reactions, I just want to give you or a reminder about what is a radical. Now, you must have a little vague idea what is a radical from your Gen Chem classes, right? Most of the times you would have looked at the oxygen turning into a diradical. And we talk about eating antioxidants like blueberries to quench this radical. Otherwise, the radicals produced by breathing in oxygen, which is like one of the byproducts or by side reactions that happen, these radicals in our bodies lead to unnecessary extra cellular growth, which form lumps and comes into a broader category of several diseases, one of them being cancer. And so probably that is where most of you would know your last information about radicals. So radicals are high energy, unstable molecules. They're definitely high energy and unstable molecules. And usually in our bodies, for example, from oxygen, they are created by the light of the sun. So the energy of the light that comes from the sun, that is the reason that radicals get created in our bodies. So these radicals definitely need heat or light. So whenever you see this delta sign, it indicates heat, and H nu, energy, is H nu. Nu is the frequency of the wavelength, or sorry, frequency of the wave that we're talking about. These two should be your clue that a radical is going to form for any chemical reaction. So whenever we had these ionic reactions occurring, so let's say you had this, and the incoming nucleophile would come, we would say there is a polarity involved in the substrate, partially negative for the electronegative element, partially positive to the atom which is directly attached to this electronegative element. The incoming nucleophile would come, it will attack the electrophile, which is the electron poor atom, and this chlorine will leave the carbon. This chlorine leaves the carbon with both the electrons. So remember, whenever a bond forms between any two atoms, there are two electrons in the bond, right? So these two electrons are taken away by the electronegative or partially negative charged atom, leaving this carbon electron poor, where the nucleophile can attack later on. So this is known as a uneven lytic cleavage. Heterolytic cleavage. Okay. On the other hand, when a radical forms, and you will see that there is a difference in these arrows. The arrows that I drew for the ionic reactions were full curved arrows. They start from electron rich, they end at electron poor. So all of the curved arrows start from the electron rich, end at the electron poor, and they are full complete arrows. But the arrows that we see for our radicals, they are half arrows. So I am not drawing this other part. This other part is missing in these arrows. So what does this arrow and this arrow differentiate? It differentiates complete movement of electrons from one part to the other, plus always it is a unidirectional flow. A unidirectional means everything happened like this. The nucleophile came in, attacked the electrophile, the leaving group left. Everything happened in the same direction. It is a unidirectional flow. On the other hand, when you look at these arrows, half of it is going this way, half of it is going this way. Be very careful when you draw full arrows, when you draw half arrows. There are certain different rules that these radicals form. So looking at this bond now, in presence of heat or light, the bond will split evenly. So this chlorine will take its own electron and this methyl will have its own electron. So one electron extra here, it would have been a bond here, but since the bond is gone, the electrons, the bond which could have been here is no more a bond. Now it has a radical. Very, very high energy radicals. So I'm going to write all my radicals like a C dot, whereas I will write all my carbocations like a C positive. Any questions on this differentiation? So this is a carbocation and this is a carbon radical. Any questions? Another important difference besides these fish hooks that we see in radicals, they never rearrange. What does rearrangement means? Whenever you have a rearrangement, you shift either a hydride or an alkyl or any other R group. You can shift those when you rearrange. So carbocations, they can rearrange, but radicals will never rearrange. Okay, so please understand the difference between ions and please understand the difference between the radicals. Any questions so far? None? Okay, so let's quickly jot down the differences that we have seen here. Both carbocations and our radicals, they are unstable intermediates, right? But in the carbocations, I have 6 valence electrons. Remember, both the electrons that were used have been taken away by the leaving group. Whereas in the carbon, I have 7 valence electrons. This is also a planar species, sp2 hybridized. This is also a planar geometry species with sp2 hybridization. For the curved full arrows, they flow unidirectionally, whereas the radicals, they form these fish hooks kind of a arrow, which are half arrows, and they can go anywhere, any direction. Carbocations always rearrange. Okay, rearrange maybe. Rearrangement. Never rearrange. So these are a few rules that you must remember. Besides this, I want you to remember, just like carbocations, now there are similarities, very much of similarities between these carbocations and carbon radicals. What is the stability order that we know for our carbocations? We know that the benzylic and the allylic are very stable carbocations, followed by tertiary carbocations, followed by secondary, primary, and then the methyl, right? Do you remember this? Why were these stable? Because of the hyperconjugation or the electron donation of groups. It stabilized these carbocations. In a very similar fashion, radicals also experience dot allylic.
It should vinyl, the lowest one.
Could you repeat that?
Vinyl.
Vinylic
Yes.
carbocations will be very, very unstable.
Yes. Okay.
So this is allyl, A, B, C. This is vinyl, when your carbocation is right on the double bond. So the vinyl and the phenyl, those are the most unstable kind of carbocations. And we'll see they are very unstable radicals also. Same exact, same preferences. And then the methyl radical is going to be the least stable among all. Then the vinylic and the phenylic. We don't even see these radicals form ever. Most unstable. Just like the carbocations are stabilized by electron donating groups and hyperconjugations, radicals are also stabilized by these electron donating groups. Any questions? Just like your carbocations are stabilized by resonance, similarly, these radicals are also stabilized by resonance. Now, please remember there's a difference between rearrangement and resonance. Whenever you will rearrange, you are rearranging a hydrogen atom or an alkyl atom, alkyl group or some other group will shift positions. But in radicals, that shift is impossible, but the resonance is completely possible. So for a benzylic, let's look at the allylic radical first. So resonance. Whenever you will have a possibility of formation of a radical, it will undergo resonance. What is the resonance that this will do? What is on this pi bond? This pi bond is made up of electrons. One electron at this carbon, one electron at this carbon. And so from the middle, I'm going to split the bond. So this is the resonance of allylic radical. Any questions so far? What did I do? I just splitted these paired electrons, and now I'm going to make unpaired electrons. This is not something that you will see forming, but just imagine something like this. Instead of now making a bond between these two, this electron wants to come here. So this electron, the free 7th electron, also shifts towards that location. I get a new bond right here. And where is my radical? At this position. Any questions on what I did? And so under the influence of heat, you will see radicals form. And just like your carbocations, your allyls and your benzylics, they are going to do resonance. How are you going to show these arrows? You have to show these arrows like splits, splitting like this. So in this case, this pi bond is splitting evenly. One electron goes here, the other electron goes here. The electron radical right here also comes together to make a bond right here. So these are just few more examples that you can look at and practice, of course, when you have your resonance practices, if you want to do that. Okay. Oops. Now we have already looked at the production of radicals, the initiators. So heat and light. These are your major sources of getting radicals into place. But the point is, which bonds will be broken? Now on this slide, I'm showing you a table, which is a table that we have already looked at in module 6 and 7. So we are going to use the same bond dissociation energy table. But the only point that is different here is that we are going to look when the bond splits. So you don't have to memorize this table. You just need to know how to use this table, how the energies have to be used. So if you look at all of these bonds, it is very easy to break the difluoride, but we rarely will use difluorination or difluoroatomic molecule for our radicals. Okay, we don't even use the iodine also. We will use chlorine and we will use bromine. Look at the energy that is required to break a primary carbon-hydrogen bond and a tertiary carbon-hydrogen bond. So if you are given a tertiary system, so this hydrogen A, and you are given a primary hydrogen B, which is going to be easier to break when you subject it to light or heat? Out of HB and HA, which will be broken first? Anybody? Out of H.
HC, HA.
Okay, very good. Because of its low energy, it will be easy to break this particular bond. And when this particular bond will break, what will happen here? A radical will form. So in this structure, we just saw where is the weakest bond. It was this carbon and hydrogen. Do you understand this? If you understand this, you will know on your structure which site will become the radical. So you can always consult this table. Look at this, peroxide. This is a peroxide, H2O2. And if you remember, we have already looked at two reagents which are doing anti-Markovnikovs. Do you remember? I hope you do remember. The hydroboration reaction, where your alcohol goes to the less substituted carbon, and your bromination reaction, where the bromine goes to the less substituted carbon. Both of these have this peroxide, which does the radical mechanism for us. And look at the amount of heat that is released. So if you are breaking or splitting up your bond, for example, the bromine, look at the amount of energy that is required. But on the other hand, if I go in the opposite direction, I have two radicals and I'm making up this bromine, then my delta H would be a negative of this number because it is going in the opposite direction. Okay, you just put a negative sign at that point. So looking at our mechanisms again, and we just discussed about this, but let's re-look at them. When you have the ionic kind of a motion or ionic kind of a group, then you use a full electron movement. So this double arrow shows two electrons moving at the same time. But when you have only one electron moving in case of radicals, then you show this half arrow or half hook. Carbocations will definitely rearrange, radicals will never rearrange. But their stability is exactly the same as that of the carbocation. The benzylic, so benzylic is usually a Y, and allylic are most stable. Vinylic and phenylic are the least stable of our groups. And this part plus the bond dissociation energy part, if you remember these two parts, how to use them, you will know which hydrogen or which bond will break when we are doing our reactions. So this is just a repetition. Electron donating groups will help stabilize your radical reaction. So where will the radical form? This is a very important question for us. Radical formation. All of us need to figure out that bond dissociation energy can help, and also the stability of resulting radical will help. So for example, the example that I had shown you earlier, where will I take the hydrogen out? Do I take it out from a tertiary location or a primary location or a secondary location? Let's look at all of these resulting radicals, A, B, and C. So let's say I don't know my bond dissociation energy, but I do know the stability of my radicals. So let's take out minus HA, that I have a secondary radical here. Any questions what I just did here? I just broke this part. Oh, this is half hook, okay? Now let me just take HC from here. So I'm going to take out my primary. The rest of it is exactly the same. I just took out the hydrogen from here. And then I take HB from here. So looking at all of these, this is a secondary carbocation radical. This is a primary carbo radical. And this is a tertiary carbon radical. Out of all of these, which will be most stable? This will be most stable. So before these two can form, this will form first. Fast forming. Whoever forms first gets the reaction done. So these will not occur. Only this HB or this product will form. So these are regioselective reactions. What does regioselective mean? The position. They know which position we are going to attack to or which position we are going to get to. In fact, radical reactions are very unpredictable usually, but they are very, very important. because the only reactions that your alkanes will do, and do you remember what alkanes are? Alkanes are plain structures. They don't have any functional groups on them. You cannot just abstract out a hydrogen from anywhere. If I have to attack a nucleophile here, can I do that? There will be no reaction. If I have to make a base here, if I put a base here, will I get a eliminated product? No reaction will occur here. So to functionalize our alkanes, radical reactions can do something to alkanes. This is the only reaction that alkanes will do. So this is a very, very, very important part of your class. All of you draw it on your notebooks. So heat. I just want you to tell me what will be the radical of this structure. Okay, I'm going to give you 2 minutes and I will call out somebody's name and you will have to show me your paper. Okay, you can pause the recording meanwhile. Think about all the hydrogens, the different kinds of hydrogens on the structure. You can also label them HA, HP or stuff. Draw out all the possible radicals that will form if you take out that hydrogen. And then out of all the possible radicals that you have formed, which one will be the most stable? All right, a few more seconds. Okay, Michaela, you can you switch your camera on? Michaela Thomas. Don't worry, you don't have to be correct. I just want to see how you are thinking about it. Michaela Thomas, can you hear me? Michaela? Okay, I guess Michaela doesn't want to volunteer, or someone else would want to. Go ahead. Larian, Clausel, do you want to share your paper with us? Okay, that's a pin drop silence. Don't be scared. I'm not grading anybody on this. I'm just trying to help all of us be on the same page. Portia, would you like to share? Okay. All right, let's not wait. Michaela, do you want to share your paper? That's fine.
Can I?
Yes, Sammy, please go ahead. Okay, so I'm going to spotlight Sammy's work. So, okay, so Sammy, we have to keep our double bond there. Okay, very good try, Sammy. I see that you made all the different kinds of radicals. but you forgot to put your double bond on there. That's a very good try. Very good. Thank you so much for sharing that. Yep. Okay. So that's a good heads up for all of us. You have to keep the main structure intact. We are not doing any reaction yet. We're just trying to make a radical out of this structure. So I can have a radical at this point. I can have a radical at this point, but both of these are similar situations. So I'm going to try it, have it here. But I know vinylic radicals are very, very unstable. So this will probably be not one of my reactions or radicals that I will form. So I can try a radical here. Again, a vinylic. This carbon already has 4 bonds. It cannot lose anything. There is no hydrogen here. So there is no radical that will be formed. So this radical will not even form. There is a hydrogen here, definitely, which you can take out, but no hydrogen at this carbon. So be careful when you're drawing your structures also. The other radicals that I can make is if I abstract out this hydrogen. Okay? And then if I abstract out a hydrogen from this location. Now looking at all of these, this is definitely a primary carbo radical. What kind of a radical is this? This is also a primary radical, but please recognize the allylic position here. So primary allylic, very stable. More stable than the primary carbocation. If there is no other carbon, this will be the go-to radical that would form. But look at this. This is a secondary allylic system. Okay, so this will be your major product. It will definitely do resonance. When it will do resonance, you will see something like this form, which is primarily exactly the same thing. So know where your radical will form. That is a very important part. If you are able to recognize your stability of the radical, then you will be able to recognize where will this radical form. So the radical mechanism, that is the next step for us. A radical chain mechanism. What does a chain mechanism mean? Everything follows. Once it starts, everything follows the other without any more persuasions. For example, when you see an avalanche happening or when you see a waterfall happening, once the water tips from this end, all the water tips behind it. Okay, you don't have to ask each drop to go and fall down. And so a chain reaction, these radical reactions, they occur in 3 phases. This is initiation, propagation, and termination. And as their names indicate, initiation just means to start or to initiate the formation of a radical, to breed or spread more of those. When you have to spread more of those, then we do propagation steps. And when you have to stop or terminate the radical reaction, that is the time that termination occurs. Okay. Now, in very layman terms, if I have to write them out, I will say that something plus something gives me a radical. Now, this something can be heat, it could be a light, or it can even be a catalyst. Sometimes radicals can also generate by catalysts. But for our course, we will only focus on heat or light. So whenever you have something neutral, something, and you have generated a new radical, there was no radical to begin with, and now you have at least one radical. That is what the initiation step is. When you have a propagation step, you have at least one radical. And in your products also, you have at least one radical. So net number of radicals and net number of radicals on either side stays the same. Of course, this will be a new radical. If this is X radical, this is now Y radical. So radicals stay the same, but who is the new radical? That will change. Number of radicals on either side will be same, but who or what is the new radical on this side, and who and what is the radical on this side, that would be a little different. A propagation, on the other hand, you will have two radicals, X and Y, let's say. Two radicals in your starting, and how many radicals in your final product? 0 radicals in your final product. So initiation gives you at least one radical. Propagation keeps spreading the radicals. So more radicals are generated, new radicals are generated. When you do termination, no new radicals are generated. So initiation, propagation, and termination. As the name has indicated, you will do homolysis. Paired electrons become unpaired. You get a new radical. This is an endothermic process. Termination, radicals combine, the chain reaction change ends. It is an exothermic reaction. But we do not consider either of these when we have to look at the overall energy of the reaction. The overall energy of the reaction comes from the propagation steps. So there might be few propagation steps, A, B, or whatever, and then you add them all together, the propagation steps, to give you the overall energy. For each reaction, you have some energy for each of the reactions. So the sum of the energy of all the propagation steps gives you the energy of the main reaction. Total number of radicals stay the same to begin with and to end with. Now, why am I emphasizing this again and again to you? Because on your exam, you might be given a few reactions and you will be asked, out of these, which is the initiation step, which is the propagation step, or which is the termination step. So different versions of exams may have that. You should be able to identify your mechanism type or the phase type that we are on. Okay? So before we do any mechanism, I want you to see what does actually happen. And just like in resonance, I had asked you to memorize 4 patterns. I will be asking you to memorize the 4 patterns in your propagation step also. Okay. In our arrow pushing, there are 6 arrow pushing steps for radicals. It is quite straightforward for initiation and for termination. So this is your initiation, this is your termination. Look at how the radicals form. Even spread. On the other hand, merging of both the radicals. It's quite straightforward. Okay, this looks like a person with the eyes and the nose and the mouth. Oh, okay, let's not get distracted. But When you look at the propagation steps, there are 4 propagations that all of us will be using again and again and again. Okay, the first of them is addition to a pi bond. So there is a radical here and there is this pi bond. You will split the pi bond. The electrons here will make a new bond with this. A new radical will be generated at this point. A hydrogen abstraction. There is a radical. There is an even split of electrons. This electron, this electron. This electron will make a new bond right here, and this bond has broken. Why did this bond did not break? Because the sigma bond stays. The sigma bond stays. For halogen abstraction, very similar to what your hydrogen abstraction is. When you have an alkyl group, alkyl radical, and you have a diatomic halogen, that's when you do this. Even split breaks the bond. Who gets the radical? The extra one which did not bond with your alkyl group. That looks very easy on paper because I'm showing you maybe that's easy. Unless you will write it on your own, unless you will practice it on your own, you will not get it easily. The last is elimination, and this is literally the opposite of addition to a pi bond. Literally, when your groups were going here, you can just do this. So that's one of the arrows that you see here. When your group was doing this, now you do this. Now you do this. So exactly opposite of addition to a pi bond and elimination. They are exact opposite arrows. What will you get? Your starting materials of addition to a pi bond and your products of the elimination. They are exactly the same. Okay, so knowing these will definitely help you, especially for the 3 mechanisms that we are going to learn. So there is a lot of reversibility in these radical processes, just like we did addition to a pi bond and elimination. The starting and the end is different, opposite arrows. Coupling, this is initiation, this is the termination, right? And the hydrogen abstraction from a alkane group or by the alkyl. Okay, so that is the only difference in here. So there are definitely reversibilities in our radical reactions. You need to understand and recognize these particular group arrows. Here we will look at the mechanism of halogenation of alkenes. So a few minutes ago, I just told you that the only reactions that alkenes will undergo is when there is a radical reaction occurring with them. Okay, whenever a mixture of any alkane with bromine or chlorine, never with iodine, never with fluorine. Fluorine is too fast, too aggressive, too violent, and it is plain explosion. Iodine is very slow, super slow. Sometimes it takes weeks to do an iodination of an alkene. So we usually will not use this. When you do your synthetic strategies, we will only be looking at the bromine or the fluorine. Okay, so whenever your alkane is heated or exposed to visible light, in presence of a bromine or a chlorine. So bromine or chlorine diatomic forms, the radical reactions will start to take place. On your exam, you will be asked which of the following is the radical steps. And you will see that I have those on our slides also. The initiation, the propagation, and the termination steps. But I want to go over these on our notebook. So, initiation. Let's do reaction between a CH3, CH2, CH3. So what do I have here? I have a butane and I have the conditions for a radical reaction. Now, on our previous information, which hydrogen will be abstracted out? There are only two types of hydrogens on this structure. Primary kinds, there are 6 of the primary hydrogens, and secondary kinds, there are 4 secondary hydrogens. Which hydrogen, primary or secondary type, will be abstracted out? First of all, you should know that. Anybody?
Secondary.
Very good. So I will choose one of these and I can just use CH, CH2, CH3. So I will use this site where my reaction will occur. So right now I'll just go and make a radical here. But don't worry about that. I just wanted to give an idea to you. So let's do initiation. When we will start to form or initiate the unpairing of electrons, you have to find out which is the easiest bonds to break. On this substrate, we found which is the easiest bond to break. And let's break our bromine also. At this point, I wanted to show you why I'm breaking our bromine and not just any bond. If we go back up here, how much energy is required to break a secondary hydrogen bond? So if you look on this text, a secondary carbon hydrogen needs 397 kilojoules per mole of energy, whereas bromine needs 193. So out of these two, who will form the radical first? The bromine will form the radical first. So even though I have shown you the site where the bromine is going to come, it is the bromine which will make the radical first. And what is my arrow that I'm going to use? The even splitting arrow. What would I get? Bromine radical. Okay, or I could also write it as 2 Br radicals, right? So that is my initiation. The next part will become my propagation. Overall, if you remember, what should happen when I have a radical and I have to abstract out a alkane's hydrogen? What would I do? I will do an even split here, and this radical will go near the hydrogen. The XH bond will form, and this R
Critical.
become a radical. Okay, so this is the propagation step that I will be using for this particular substrate. So I have identified first which hydrogen I'm going to take out. So CH3, CH. I'm just going to draw my other H like this. Plus the bromide radical. Okay, I just wrote my radical here and my HX is here, but same stuff will happen. Even splitting occurs. This radical goes here, CH3, CH radical, CH2, CH3 plus HBr. So now look back. When I had initiation, I had no radicals to begin with, but now I have radicals. And that's what initiation step is. No radicals in the starting material, but eventually you have some radicals. In the propagation, what do I have? How many radicals do I have here? I only had one radical. And in my products, how many radicals do I have? I still have only one radical. But who or what is my new radical is different from what I had earlier. So this, if you are given a structure or a reaction like this, you must be able to identify that there was one radical here, now there is one radical here. So I have not formed my product yet. The next propagation step that I will be using is when I will do the dehalogenation. So I have the alkyl and I have the diatomic halogen. What is going to happen? Cleans uneven, even splitting. This R going towards the X, one of the halogens. What would I form? Rx plus the halogen. So this is the common propagation step. So where is my R radical? It's right here. CH3, CH radical, CH2, CH3 plus. Now remember, when I show you this reaction, there is not just one molecule of butane or one molecule of bromine. There are millions and millions, several molecules in that one flask where your butane, where your alkane and your halogen will be there. So we have already consumed one bromine molecule. We will now be using another bromine molecule. So whenever you do alkane and halogenation, we usually take our halogen in excess so that we can get a good product. So splitting, going towards here, CH3, CHBr, CH2, CH3, plus what? Another bromide. What would this bromide do? It will go and attack another molecule of butane, and the propagation step will keep repeating here. So these are the two major propagation steps that we use for this mechanism. There will be other propagations, there might be other propagations going on, but these are the useful propagations that we need to see. This is the useful initiation that we need to see. Okay, I'm not saying that there is no chance that this carbon-hydrogen bond will not break. Maybe those radicals are also forming, but they are not very in a large amount, or they will not be very useful for our mechanism. So for our mechanism, this makes more sense. Similarly, the last step will be termination. Now, before I tell you the reactions that are useful for termination, one thing all of you must remember is there has to be more initiation, more propagation than termination for a successful chain reaction to occur. What does that mean? there should be less radicals reacting together to terminate the chain, right? It makes sense. If more radicals, what if the bromide was just attacking together and they would just form the bromine again? Would any reaction occur? No. What if these two guys were reacting together? So this radical with another R radical was reacting together. Would you form the desired product? No. So your termination should, the rate of reactions of termination reactions should be very, very small. Okay? So one of the termination reactions that will be useful for our reaction is when you have one of these radicals and one of these radicals. When they will couple. Okay, so this is just the opposite of our initiations when you have an even split. This is your pairing. The unpaired are now being paired. And you are getting a useful structure here, which is our final product. Now, I'm not saying that this is the only reaction that would occur. Other side terminations will also be occurring. For example, the bromine and bromine will be reacting to terminate. These two radicals may be reacting or coupling to terminate the reaction. But those other materials are not useful for our mechanism. What is useful for our mechanism are these steps. Any questions? No questions? Okay, perfect. So all of these chain mechanism and reactions that we almost saw are on these slides. The only different thing that we see here, and these are the different kinds of reactions that I wanted to show you. When a bromide couples, when these alkane halides will couple. So overall, the stability of the reaction, if you look, we have to add the propagation steps. If you add all of this, you see that you still have a delta H negative. And so even though it takes a lot of time and a lot of energy to start these reactions, overall stable bonds form. Okay, because overall delta H is negative. Okay. Please remember, these are the only reactions of alkanes. There will be no more reactions of alkanes that can functionalize a group. So on your exam, or if you see a reaction like this, let's see. How are you going to do the synthesis? What reagents are you going to add so that you get this particular product? So think about your synthetic strategies. What is the number of carbons? The number of carbons in both of these are exactly the same. What is your functional group transformation that has happened? From no functional group, your molecule now has some eliminations. What kind of elimination is in your product? So you think about, is there a rearrangement? If there is a regiochemistry, what is the positioning of your groups? What is the stereochemistry? Do you see an inversion or do you see racemic mixtures forming? So regiochemistry is the position. And regiochemically, we see that this is a Z-SAS alkene. How do you make a Z-SAS alkene? What do you use to make a Z-SAS alkene? You definitely need a less bulky base, right? And what is the substrate that you need? You will need either a leaving group here, or you will need a leaving group here. Why? Because these are the only two carbons where your double bond will form. This leaving group, if it goes with sodium ethoxide, forming a double bond here will be difficult because it will be a Hofmann product. Similarly for this, no double bond will form here with sodium ethoxide because a double bond cannot form here. It will be a Hofmann product. So for both of these starting materials, your sodium ethoxide will give you a double bond right here. But how do you functionalize an alkane? If you have to functionalize your alkane, you need to have a halogen here or a leaving group here or a leaving group here. Where is it easy to get the leaving group? At the tertiary location. Why and how? When you will do your bromination, H nu, which carbon site's hydrogen will be abstracted out? The secondary or the tertiary? We know it will be tertiary. So where will the bromine go? Bromine will go right here. So what kind of a leaving group did you form? You formed this kind of a leaving group. Now when you will put sodium ethoxide, you will get your ZSAVs product like this. Any questions? Okay, so think about your synthetic point of view also. Any questions so far? No questions? Okay. Now the next part of this halogenation mechanism is that brominations are more selective than chlorinations. So remember, first of all, halogens will only undergo a bromination or a chlorination, never iodination, never fluorination. And among the brominations and chlorinations also, bromines are highly selective. So if you look at this example from the primary, secondary, tertiary, it is a tertiary site where your bromine will be attached. You don't have to worry about the minor products. On the other hand, chlorine, being a smaller atom, more reactive atom, we see that tertiary and chlorine, secondary and primary, they are going to form in competition. They will be competitive. You cannot decide who is the major product. Why? Because there are 6 secondary hydrogens in this structure. In this structure, there are 6 secondary hydrogens, and practically all of those secondary hydrogens can be replaced by chlorine. Similarly, there are 9 primary hydrogens on the structure, and all of them can be replaced by the chlorine. There is only 1 tertiary hydrogen on this structure. So there is only going to be 1 kind of a structure here. So if you look at the probabilities, it is the secondary site that would have more probability of chlorinating in this particular structure. So remember, whenever I will ask you to do chlorinations, the only synthetically useful halogenations that you must do are with bromine. Okay, so another example just for all of us to see, there is the tertiary substrate, definitely major, but 28% of other structure is still possible. But on the other hand, for bromination, literally only one product forms. Now with chlorinations and brominations, we also have to remember that stereochemistry will occur, because once the radical forms, radical is a flat structure. Chlorine can attack from one side, chlorine can attack from the other side also. So you will get equal amounts of the enantiomers. Well, this is not an enantiomer, but enantiomeric site is right here. So this is one of the problems that we face with chlorinations. So major product is not only dependent upon the rate of the reactions and the number of hydrogens with the probability of exchanging with the halogen. Okay, these energy diagrams just show you that because the rates are so close, we cannot determine the major product easily with chlorines. Chlorination of alkanes, you have to show all the products that are possible. Okay, so stereochemically, all the products, primary, secondary, tertiary, all those products also, you have to show them with chlorines. So brominations are slower and hence more selective, because it knows, bromine knows, I have only one shot to abstract out a hydrogen. Let me use it to take out the weakest of the carbon hydrogen bond. Chlorine, on the other hand, is very fast. Okay, so if you look, bromination, the first step is endothermic. Okay, that is your rate determining step. So this is an endothermic or an exothermic reaction. Overall, it is an exothermic reaction overall. But the first step is the rate determining step. If you look here, in here also the first step is the rate determining step. Overall, it is also exothermic. But in bromination, the first step is endothermic, which needs more heat. So it is a little slower. So bromines are slower and selective, whereas chlorinations are non-selective. They just vigorously happen. And imagine what would happen with fluorine. We cannot even control it. So according to the Hammond postulate, the differences in the radical stabilities are reflected at these transition states. So these are your transition states. So the transition states energies and the products which form. Okay, so that is what your dependent upon your rate. So you can see the energy differences here. The first product, which is rate determining, has very same energy as the second one, but that energy is different in chlorine. Overall, the fact is chlorinations are not synthetically selective. You have to be careful. Don't use chlorinations when you're doing halogenations of your alkanes. Also remember your stereochemistry. Racemic mixtures will happen with chlorinations and brominations. With chlorinations, you will get more amount of products, more number of products. Okay, any questions so far? Okay, this is again reminding you that no halogenation will occur with iodines or with your chlorines. Okay. So where will this reaction occur? So remember, where is the most stable radical will form? The most stable radical in this particular state will form at the allylic site. This allylic site or this allylic site. Which of these will be the most stable? This is a tertiary allylic site and this is a primary allylic site. So we are only going to focus on this primary allylic site. There is no rearrangement, but whenever you will have an allylic structure, you will see resonance occurring. How will you see the resonance? Pi bond splits, the radical forms a new bond here. Right? So this will be one of the propagation steps. And so from both of these, I'm going to form product. So when you look at the mechanism, or what is the type of product that this reaction can give you, both of these products will form. Okay, so remember, sometimes I give you this reaction, predict the product of the following reaction. What if I don't give you this product? I only give you this product. Then you should know how this product was formed. Not from here, but from here by resonance. Okay, so knowing your resonance structures and knowing your mechanisms, knowing where the least stable hydrogens are, it'll be important for you. Now this example has actually set a good stage for us for allylic bromination, which is a very important kind of reaction that we have seen. So far we have only seen two reactions, halogenations of alkanes, and now we are going to see the allylic brominations. Okay? So when you look at this, oops, I should have written a bromine here. When you look at this particular reaction, there is an allyl, no doubt, but there is heat, no doubt. But what another reaction we have seen with bromine and alkene? We have seen the electrophilic addition reactions. What happens in those electrophilic addition reactions? Markovnikov's and anti-addition reaction occurs. So this electrophilic addition reaction can compete with this particular reaction, right? So to avoid formation of this side product, this unwanted product, newer conditions were created in order to do halogenations on allylic sites only. But in these new reactions, we do not use the diatomic bromine anymore. Okay, what we use is the N-bromosuccinamide or NBS. So when you are doing your test, if you have a quiz or if you have an exam where you have to write out, then you can write NBS. Recognize the structure of NBS. N is for the nitro, B for the bromo, and the succinamide. It's a 5-membered ring, 1 nitrogen, 2 carbonyls on it. Now, instead of having the dibromo kind of a entity, we have our just bromine. So the amount or the concentration of bromine that we are releasing is very small. So the reaction will not occur here, it will occur here. That is the only thing. So moreover, allylic position of alkene is definitely the best place to form a radical because of resonance stabilizations. The bromine necessary for this radical to form comes from N-bromo and HBr. So you definitely need this particular initiator. So peroxides will act as a great initiator for your reaction. You don't need to know the mechanism of this. You just need to know the conditions. You have NBS, you have HBr, and then you have the peroxide. It could be R, it could be O. And of course, the heat in your reagents. So whenever you will have these conditions, always make sure that you do a allylic bromination. This is your major product, not this. Of course, this is the side product that forms, but you don't have to worry about that. Okay, so this is just more examples where you have NH with NBS. And how did this product form? From resonance, right? So you have to remember this. Whenever you will see the allylic and you will see radicals, resonance of the radical structures will happen. Also, the minimization of the concentration of HBr or bromine definitely ensures that we get a radical bromination of the allylic or the benzylic system. So NBS and H nu or heat. What is the only product that I will see here? This is going to be the most stable radical, plus it will have the resonance structure right here. So both of these will form with my benzylic system also. Okay. The last mechanism that all of us need to know from here is the boration. Oh, first, before we do that, let's go with the anti-Markovnikov addition. Okay, you know what? Let's start that those two mechanisms tomorrow. What I would like for all of us to do today is to decide what would be a good time for our exam would be. Okay. What should be our uh, 8 a.m. 9 a.m. Actually, let's not do that. Okay, so before I give you this poll question, I just want to remind you, that there are only two choices. Either 8 a.m. of that class or 10 a.m. of Saturday. These are your only two choices. The other thing that I want to mention to you that if anyone has, even if it doesn't matter if 10 students say at 10 a.m. and one student says at 8 a.m., then we will have to think about if we can shift depending on what is the problem for that student. You know, that may be a clash of other exam also, because if not, then we'll just have it at 10 a.m. of Saturday. Okay, but I just want all of us to be on the same page. Okay, so I'm gonna launch the poll. And all right, I think everybody's done choosing the sides. Okay, so all the students who have a problem with 10 a.m., there are 3 students who have problems with the 10 a.m. Could you please send me what your reasoning is? If it is a genuine reasoning, I will think about all of that also. Go ahead, you can privately send it to me via chat. We still have a couple more minutes for the class to end. Oh, or is it done? Is it one? Still 2:28. So if you can do it right now, so we will decide it right now. And I have one more student. Okay, I'm waiting on to that one student who has not replied. I see. Okay, I see what everybody's reasoning is. And I'm responding to them right now. Oh, I should stop the recording.